welcome. We will talk about Moscow Heat Island and other things, of course. So thank you. The floor is yours.
Thanks a lot for introducing, and thanks a lot for waiting during this pause. I will tell about not about citizen science, but about machine learning, which often comes together nowadays with citizen science. So I hope that this talk will be relevant for this section. So, few words about motivation. It originates from modeling. Yesterday we heard that now we have very good urban climate models, urban parameterizations, but all this stuff is computationally expensive, especially when we would like to have high resolution. And more attention is nowadays to machine learning models, which is a kind of statistical models. And our group is not exception. We also try to use this novel approach for Moscow. And this is the general idea of our project. We would like to combine several kinds of observations, large-scale data, for example, reanalysis, detailed descriptive data, to provide real-time downscaling and data fusion. And the feature of this project is that we would like to use results of hydrodynamical modeling to train the machine learning-based models. And my presentation will include two parts, two problems. The first problem is approximation of temporal dynamics of heat island intensity observed at one side, but for a long period, using machine learning and using predictors characterizing large-scale weather conditions. And second part will be about approximation temporal and spatial variations of heat islands simultaneously. So let's start with the first part. It's so-called one-D regression because we have our target variable observed only in one place. It's a purely urban weather station in the center of Moscow, and we would like to approximate observed heat island intensity using predictors characterizing large-scale weather conditions for Moscow region. We use two types of data source, observations averaged over 9 rural stations, and or reanalysis. And we use two approaches. First approach, when we predict observed VHI intensity using predictors for the same time moment. And another approach, we involve additional features characterizing delayed connections between our target variable and predictors observed in preceding time moments. So there is a list of predictors. There are basic variables such as 2-meter temperature, wind speed, cloudiness. We also use empirical weather factor suggested by Tim Oak in the end of previous century, which is empirical function from wind speed and cloudiness. So we use a data set consisting of 3 hourly data for 21 years, quite a huge amount of data, and we use standard k-fold cross-validation technique. And we compare several machine learning-based models. The baseline model is linear one, and we compare several tree-based models, random forests, gradient boosting, another version of gradient boosting developed by Russian company Yandex, and multilayer perceptron, which is a simple artificial neural network. Here is an example how this model works. This is the baseline, the linear regression, and on the upper row we see model model versus ground truth for data sets without temporal features. So a prediction is made based only instant moments and only observations, only reanalysis, and using both types of data. And we see that model quality improves when we use both types of data simultaneously, and improves when we use temporal features characterizing delayed connections. And this is the best model, can boost regression. So you can see how the data cloud changed. And this is a neural network. Here is a bit different shape of cloud, but not the best quality. So the best quality is reached by this model. And there is a comparison of all models and all their configurations with different hyperparameters. We try a lot to achieve good results with neural network, but surprisingly, it outperforms only the linear regression. And the best results are reached by decision trees models. And the absolute leader is can boost regression, and it is also the fastest model. Uh, so all these trainings were performed using personal laptops, so all of them are quite fast, but this is the fastest. And this is a more detailed comparison for two specific periods, winter period and summer period. The variable is VHI intensity, and in summer it has pronounced diurnal cycle. In winter is driven by synoptic scale processes. And we can see how good our models capture this dynamics. And these periods are also interesting because they allow to compare results of machine learning based model and dynamical models, specifically with of high resolution simulations with Cosmo mesoscale model and TerraUrb canopy scheme. For these periods, we have simulations. And surprisingly, ML-based models outperform this dynamical model by 40% in winter and 21% in summer. And advantage of ML-based models is opportunity to analyze importance of predictors, and these are results for different tree-based models. And we can see that most important predictors are when we have only observations. The most important predictor is empirical weather factor. And another important predictor is 2-meter temperature, and specifically its tendencies. Tendencies during previous 12 hours. So our temporal features consist of tendencies and moving averages. I forgot to say it. And when we have only reanalysis, the most important predictor becomes the boundary layer height, and again 2-meter temperature tendencies. And when we have both types of data, we again have important predictor of weather factor, boundary layer height, and 2-meter temperature. And now very quickly part number 2. Here are only preliminary results. We approximate temporal and spatial variability simultaneously. And here we use as ground truth results of Cosmo simulations for one summer with 1 kilometer resolution with TerraUrb urban canopy parameterization. And here we use the same model architecture, so this quite simple approach, no complicated neural networks, only the simple tree-based can boost regression, which performed in the best way from the first part. We use area for this test 70 by 70 grids and we use again as predictors large-scale meteorological conditions. from smooth Cosmos simulations or from error interval analysis, which was used to drive the Cosmos model. Special features, I will talk about this later, and some astronomical predictors such as solar height, day fraction, and so on. And the key challenge there is how to approximate spatial variability of the urban heat island. And we use this idea that urban heat island intensity is a fixed point, is shaped both by local scale surface properties and mesoscale settings, position of this point within the city. Previously, we have investigated this issue using citizen stations and get some interesting results, but it is another story. And so to take this into account, we take the local scale heterogeneity described here by only one variable, urban fraction, which is used to define tiles in the model. And firstly, we smooth it with different window size and also shift this window size. So this is to take into account diffusion, and this is take into account advection. And these are results. So this is ground truth, simulated urban heat island. And these are results of machine learning based models for different settings of spatial predictors. So no information about spatial predictors, information about local predictors, and here we take into account diffusion, and here we take into account advection. And this is animation, and we can see that this image is agrees in the best way with ground truth. And the last example, so this images demonstrate this example shows that here we capture only local scale effects, and here we capture diffusion, and here we capture also OHI advection. So this is actually I'm going wrong side. So this is my conclusion. It's in the slides. So for the first part, we will soon have paper published, and second part is under development. So stay tuned. Thank you for your attention.
Thank you for your nice presentation. There's plenty of time for questions now. Yes.
Thanks, Mikhail, for the presentation. Just a precision, how do you move? I didn't properly understand. How do you move your city? It's dependent on the wind direction that comes from Cosmo, or how do you choose where to move that? Do you do it randomly, or?
For now, we move the city in 8 directions. Here I show only 4 directions. We move it in 8 directions and include all these fields as predictors.
Okay, and then you want, okay, the model does the rest of it. Okay, thank you.
More questions? I see.
Sorry, I just hold the mic. Sorry, simple question maybe. On your time series where you showed the heat island, you had a really large heat island in the winter. Synoptically work?
Yes, Moscow is known as the world's coldest megacity. So when we have frosts in winter, we could have quite strong heat island, mostly because of house heating, and also because of stable boundary layer. And this is not the strongest winter heat island. We could have up to 12 degrees in winter.
Okay, so it's driven by anthropogenic heat. Does that have any impact on your ability to do machine learning when the underlying processes are completely different, but then the size of the heat island is about the same in the sun?
Yeah, there are of course completely different physical processes, and this is and because of this, it's especially good that model perform quite good both in summer and in winter.
There was another question. Yes.
Yes, thank you. I'm wondering if the model is only trained using clear sky conditions, or how do we account for cloud cover? In particular, if cloud cover would be differentially, I mean, there has been some studies that cloud cover is differential across large metropolitan areas under those conditions.
No, we train the model over all data, including both clear sky, cloudy sky, intermediate conditions, and we use cloud fraction, total cloud fraction, and low cloud fraction as predictors. And we also use when we have reanalysis, we also have radiation fluxes as predictors.
Okay, but to clarify, this cloud cover fraction is a one value for the entire domain?
Yes, it is one value for entire domain. This is the general idea, to have the large scale predictors.
So when moving the city to account for advection, how do you decide on how far to move it?
Actually, there are now several empirically based values. So we smooth with some windows. There is size of window, and for each window size, when used for smoothing, we shift the field by the same value in all directions.
Okay, so you don't take wind direction, wind speeds into account.
Wind speed is also included into predictors, so the model. So we expect that model will do its work and will understand how to connect wind speed with these fields.
So since you've already worked with crowdsourced or especially NetApp data, have you considered using this also as training data for this?
Not yet, but it is our general idea of the project assumes that we will now train the model using numerical simulations, and then we'll make a data fusion also involving probably NetApp data.
Thank you.
Thank you for the questions.
Thank you, and we thank all the speakers. And thank you for attending this session. And now it's coffee break and time for this.